So you recall that our analysis of production is the mirror image of our analysis of consumption. But instead of calling the curves in different curves, people now call them isoquants. Then rather than looking at inputs into consumption, people look at inputs into production. So here's steel and aluminum. Here's our isocost line, the same as the budget constraint in consumption. So at the intercepts, if you're not buying any aluminum, you're spending all the money instead on steel. So this intercept is N, the total amount of money that you're spending on an input divided by the price of steel. And likewise for the vertical intercept. And divided by the price of aluminum. And then our goal is to produce as many cars as possible, given that we have only N value to spend on our inputs. So we move to higher and higher isoquants, each isoquant being characterized by a given level of production. So, for example, on this isoquant, maybe you're producing 10 cars. Then on this one, 20 cars. More first because we have more inputs available. And then as well, the higher isoquant, all input bundles that can produce 30 cars. However, you don't have enough money to produce 30 cars. The best thing you can do is to produce 30 cars. So we maximize production by finding the tangential point where the slopes are the same for the isoquant line and the isoquant. At the transiency, the relative price of steel is equal to the marginal value of steel to the firm relative to aluminum. That is the marginal product of steel relative to the merchant product of aluminum. And there we are. And then a final bit of information is the production function for producing automobiles depends on steel to the power of 1/2 and aluminum to the power of 1/2 as well. Okay, so now let's determine how much steel we wish to buy and how much we can produce with the optimal amount of steel and aluminum. So now it would be helpful if we use some calculus in this problem because we want to derive the marginal product of steel and aluminum and then to equate that ratio up to the relative price of steel. So if you have not yet had calculus, or if your calculus is a bit rusty, no problem. Really, all that we need is the power rule in this case. So what is the power rule? Let's begin with a function a that is equal to a constant a times x to the power b. In this general rule, the derivative, there is a change in y relative to a small change in x is equal to b times a times x to the power of d minus 1. So for extra credit, consider this example for y, 2x to the power 3. What is the derivative in this case for extra credit?
It is 6 multiplied by x squared.
Yeah, so all we have to do is to apply the general power rule. All right, so now we can apply the rule to determine the marginal products of steel and aluminum in producing automobiles. So notice that with respect to steel, with respect to S, in this derivative, we will treat the expression for A as a constant. So we have a to the power 1/2 of putting the part of b in our original power rule.
Professor, I wrote the answer in the chat.
I'm sorry, I did not hear
I
you.
wrote the. Sorry, I wrote the answer in the chat. The derivative for dqds.
Oh, in chat. Okay, good. So just for reminder, the general power rule is BA times X to the power of B minus 1. And now you can provide us with your answer from chat, Levi, for the multiple product of steel. So we will treat the expression for A as a constant in this derivative times 1/2 the power of X in this case. Times S to the power of negative 1/2. So it looks a little bit messy, but we'll see that things to simplify once we're looking at the ratio of the Mercer products. And then by symmetry, the derivative with respect to aluminum is treating this time the expression for S is a constant times 1/2 times A to the power of minus 1/2. Yes, that's correct. So at the tangency, the price ratio is equal to the merger product ratio. I should have a minus sign right here. So let's see. here is the numerator for the marginal product ratio. And then multiplies the marginal product of aluminum in the denominator of that expression. So let's see, we have 0.5 times A to the power of 0.5 divided by S to the power of 0.5. And the numerator. And then in the denominator, 0.5 again times S to the power of 0.5 divided by A to the power of 0.5. So that looks better messy. But let's clean it up a bit by getting rid of the 0.5 in both the numerator and the denominator. So in the numerator, we have the ratio of A to S to the power of 0.5. In the denominator, the ratio of S to A again to the power of 0.5. So notice that we can take the inverse of the ratio in the denominator and express the inverse in the numerator. So there is the numerator once again. And now let's invert the denominator. So this is A over S to the power 0.5. Or very simply, A over S, since they add together the powers of 0.5 in both cases. And there is the, initially, that is 10% booking term for the marginal product ratio that turns out to be very simple. Okay, so let's now express the temperature point. The price ratio is equal to the ratio of marginal products. And we have a very simple expression. The amount of money spent on steel equals the amount of money spent on aluminum. So you can see that we have multiplied through by S and then multiplied through for the price a day to get this expression. So we're making progress. Our input demand functions for steel is the price ratio of ton per A to aluminum times A. We are almost home. However, our demand functions for steel should not depend directly on aluminum, but instead on the amount available for spinning M. But from our isocross line, we know that M is equal to spending on steel plus spending on A, aluminum. So this solves for A. And dividing through both sides by the price of aluminum. And there is an expression for A that depends on prices and on M as well. And by the way, notice that this is also the function for our isocross line. All right, good. So let's plug in our expression for A into our input demand function for steel. Oh, I'm sorry, I didn't mean to wipe that out. So going back to our derivation from the point of tangency, solving for steel, and then substituting for aluminum by using our isocross line. Okay, and now you can substitute this expression for A into our function for S. So extending this expression will actually simplify matters, although it may not be evident right now. Now adding S on both sides, and on the right hand side canceling out the pressure of aluminum on both sides. We have remaining on the right hand side and divided by the price of steel. And then finally, there is an input demand function for steel. And this is the M divided by 2 times the price of steel. And then by symmetry, the same idea for aluminum. Except that it depends on its own input price rather than the price of steel. So notice that spinning on steel is equal to or total spinning of M, 1/2 of that amount. And the same thing for aluminum as well. So there are input demand functions for steel and aluminum that are interesting, that for both functions are so simple that they do not reflect the cost price, only the own price for that particular input. And I believe that that is the answer for the extra credit problem. Yes, they definitely have it. So the final question is to uh, uh, calculate the number of automobiles that they will be producing, given that N is 100, and that the price of aluminum and the price of steel are 1. So this is what we have, bearing in mind a production function. And it's 100, and the price of aluminum equals the price of steel of $1. So to calculate the number of automobiles that we are producing, we will need to first calculate the amount of aluminum and steel that we are using. Using our input demand functions for steel and aluminum, we have the steel is equal to 100 divided by 2, and then the price of steel is 1. So we are using 50 tons of steel. And the same thing for aluminum. Again, let's specify aluminum using a different values for N in the price of aluminum, or 100. Again, divided by 2. So what is Q? So add 2 points of extra credit. Using our production function. A is 50. To the power of 0.5. And S is 50. Again, to the power of 0.5. So what is Q? And that's right. Q is just 50. So what looks like an incredibly complicated problem turns out to be very simple to solve. Questions about that exercise? If you had had if you have had calculus, you can solve the problem in another way. Not required for this class, but they just provide you with an alternative. So this maximize production are given, but basically is a budget constraint. So to do that, let's use our production function for automobiles. And then introduce a constraint that reflects the fact that we cannot spend more than M on both inputs. And we will maximize that expression with respect to both inputs. So we'll call the entire expression L after Lagrangian. And we will differentiate L with respect to S as a first order condition and set that equal to 0. And the same thing for aluminum as well. And then finally, C, which is a multiplier in this problem, is also a choice variable. Divide the first order condition again, but this one is very simple. It just says that then is equal to full spending on steel and on aluminum. So you can solve the problem this way rather than to solve it directly from the print advantage. This will work as well for the necessary conditions. And we need to do that on the midterm, that is used the function rather than the derivation to the print advantage of the digit extra credit. Then that takes care of the problem. Questions? So much for problem number two. Okay, so would you like to turn now to problem number three? So this is a profit function that we will derive for a monopolist, that is for one producer who is dominating the entire market for automobiles. So the inverse demand function for automobiles is expressed in terms of prices. 300 minus Q, where Q is the number of automobiles sold. And then we have a marginal cost function of just 2Q. Now, before we solve the problem, which turns out to be very easy, here's some background to remind you of the theory of monopolies. Let's consider first not of a monopoly, but instead a competitive firm. That is a firm that must take as given the price determined in the market. To maximize profit, that firm has an easy solution. It will produce each automobile as long as the price it receives on the car covers its cost of production. So here's the price of automobiles set by the market, not by this particular firm. And here is the marginal cost function for this firm. So this is IBEX firm. that wants to maximize profit, he could do this by producing each automobile for which he is paid more than is necessary to cover the cost of production. So in this case, that could produce, let's say, 5 automobiles. He is making profit on each car because the price covers the marginal cost of that car. But why stop there? Let's continue to produce cars until we just barely break even on 100 cars right here.
I'm sorry, Professor.
Uh-huh.
May I ask a question?
Yes.
Why is marginal cost a curve? It should have been a straight line, shouldn't it? Because it is.
That's a good question. Normally, marginal cost in the short run will rise with additional production because we are overusing our fixed input. So, for example, suppose that you are selling pizzas and you have one oven. With that oven, you're not able to produce more and more pizzas at the same unit cost because eventually you are congesting the area that has the oven. In the beginning, only one of your workers is using the oven, and that's fine. But if you have 5, 10, 15 workers in a small room with one oven, many of those workers will not be able to produce because they don't have an oven for each worker. Therefore, the cost of producing pizzas is going up because you have to pay wages to every worker, even though most of those workers are idle.
Thank you, Professor. So this means that no, it doesn't. That the function of the marginal curve doesn't really matter. It's always concave up.
This, usually that's the case, yes.
Thank you, Professor.
No, I mean,
Sorry.
of course, there is in the real world other examples. For example, for the internet, most of the post is actually going down rather than up because once you have created the web page, it is very easy to replicate the page for more and more consumers. For the internet, we actually had descending marginal cost. And that is probably the main reason why the internet is dominated by very large firms, such as Facebook and Google and Apple. But right now, people stick to the conventional pace of a rising marginal cost.
Thank you, Professor. I understand.
So let me summarize that discussion. marginal cost usually rises because they eventually use up the fixed inputs. But the one element is the pizzeria. The price function, however, is a constant because the firm cannot influence that price. So in short, the net gross profits of that will produce up to the point that the price equals marginal cost. In this case, for 100 automobiles, there is no point in producing any additional automobiles because the marginal cost is greater than the price received. And then one last point to note, for the competitive firm, the price is marginal revenue. Each time that I sells a car, he receives a price of 1 million pennies. So the price is also his marginal revenue. The amount of money that he takes in for each additional car. So another way that we can express the rule for maximizing profits is to produce up to the point that marginal revenue equals marginal cost. And that is the rule that we will apply in the case of a monopoly.